In the previous lecture, we have seen the concept of partial waves in solving the scattering problem. Or you may call, we have discussed actually the partial wave analysis. But in that lecture, you have learned that the method of partial waves is limited to the case of low energy scattering by the short range central potentials or the spherically symmetric potentials. Okay? So, what will happen when the potential is not of short range, it is not of central nature, or the spherically symmetric potential, and energy is also high? So definitely when you talk about the non-central potential, okay, high energy of the incident beam of particles, then definitely you can't apply the method of partial waves. Actually, in this condition, an approximate method, which is called actually Born approximation, that is the appropriate method to deal with the scattering problem in such a situation. So you can say that if potential is not necessarily central and energy is high, then a scattering problem is solved by an approximate method which is called Born approximation. Okay? Actually, in this lecture, we are going to learn about this Born approximation. Okay? This is a very important concept, and this video will be very helpful to you for your examination purpose. Okay? In fact, in this video, we will first of all see how we can calculate the differential scattering cross section, okay, by applying the concept of Born approximation. And after that, we will learn what is the condition for the validity of this Born approximation. It means this Born approximation is not always valid to deal with the problem of scattering. So, what is the condition under which this approximation is valid to solve the scattering problem? That is a most important fact. And whenever a question regarding this Born approximation will be asked, definitely you will have to ask this condition, definitely. Okay. So now let us see this O I have considered as an arbitrary origin, and here there is a source of potential, you can say, and from of this source of potential I have considered here an elementary volume which I have denoted by the symbol d gamma double dashed. And with respect to this arbitrary origin O, the position vector of this source or this element, you can say, is r double dashed. Okay? And this P is actually the point of observation where the effect of this potential after scattering will be observed. So this is called point of observation. Okay? And I have shown in this figure that this R is the radius vector or the position vector of point of observation relative to this arbitrary origin. Okay? In fact, before this lecture, in the beginning of my videos on this scattering problem, I have discussed in detail the Green's function. And why I have discussed the Green's function, now you can see the cause. As I have definitely told to you that whenever we will discuss the real problem, real theory of scattering, we need a concrete knowledge of Green's function. Actually, the total wave function of the scattering problem can be written in terms of the Green's function. And in fact, the total wave function, if you denote it by the symbol psi of r, then if the source point is at the point r double dashed, then this total wave function is given as e to the power I k dot r minus m over 2 pi h bar square integral of g of r comma r double dash v of r double dash psi of r double dash d double dash. Actually here you know this g of r comma r double dash is the Green's function, and this v of r double dash, this is the scattering potential, and this d gamma double dash represents the elementary volume. Okay, and here this psi of r double dash this is the wave function at the position r double dash. Okay, and this psi of r denotes the total wave function, which actually consists of both the incident wave function and the scattered wave function. Now if you will replace this vector r by, let us say, r dashed, then what will be the form of this equation 1? You can simply write, instead of r we will simply write r dashed. So this equation 1 under this assumption will become like this. This is psi of r dashed is equal to exponential raised to the power I k dot r dashed minus m over 2 pi h bar square integral of g of r dashed comma r double dashed v of r double dash psi of r double dash d double dash. Okay. Now if we want to write the total wave function of the source point, which is located at r double dash, not at r dash, not at r double dash. So see this figure, this is again the arbitrary origin, but now the source point is located at r dash instead of r double dash. So in this condition, if you want to write the expression for the total wave function, keeping the source point at the position r dash, then this psi of r will be what? Actually in this equation 1 we will only replace r double dashed by r dashed. Okay, then we can find the total wave function when the source point is at r dashed, not r double dashed. Okay, so on the basis of equation 1 you can write psi of r now is e to the power I k dot r minus m over 2 pi h bar square integral of g of r comma r dashed. You can see instead of r double dashed I have written here r dashed. Okay, and v of r dash psi of r dash d gamma dashed. Okay, now in fact the value of this psi of r dashed, which has been defined in equation 2. Now let us substitute this value of psi of r dashed in equation 3. Okay, so see when you will write the expression for psi of r using equation 2 in 3, the first term in RHS will be e to the power I k dot r. Okay, and in the second term there will be m over 2 pi h bar square integral of g of r comma r dashed v of r dashed, but instead of this psi of r dashed you have to write this much. Okay, which is the RHS of equation 2. So inside the integral there will be actually two terms. First one will be g times g of r comma r dashed v of r dashed times this exponential e to the power I k dot r dashed. Okay, and d gamma dashed. This will be the first term. And the second term, in second term you can see this m over 2 pi h bar square and this m over 2 pi h bar square will be multiplied, and both terms are negative, so this will become positive, and that will be m over 2 pi h bar square whole square. Okay, and now this term, this integral term will be written. So you can see I have written it here. This is easy to see. Psi of r is equal to e to the power I k dot r minus m over 2 pi h bar square integral g of r comma r dash v of r dash e to the power I k dot r dash d comma dash. And the second term is this much. This is m over 2 pi h bar square whole square and double integral g of r comma r dash v of r dash g of r dash comma r double dash v of r double dash d tau double dash d tau dash. Okay. Now actually we will now interpret this equation 4. What the different terms of equation 4 actually implies. Now let us see this. Actually, when you have obtained this equation number 4, actually this equation is obtained by the process which is called iteration. By the process of iteration, this equation 4 has been obtained. And so that this equation is called the first iterated form of this equation 3. So equation 4 is what? This is the first iterated form of equation 3. Okay. Now, see the different terms in RHS of equation 4. When you will talk about this first term, which is e to the power I k dot r. Actually, you know, this first term in this first term e to the power I k dot r, this actually represents the incident wave function. Okay, e to the power I k dot r represents the incident wave function. Actually, k is the wave vector of the incident wave. Okay, but the other terms represent the scattered wave function. Okay. Other terms correspond to the scattered wave function, you can see. In fact, the first term in the scattered wave, you can see here. This first term, which is actually integral of g r comma r dash v of r and this much. Okay. Actually, this first term in the scattered wave represents the single scattering of the incident wave e to the power I k dot r dashed. Okay. This e to the power I k dot r dash, this is actually the incident wave. Okay. And this has been scattered. Okay. This has been scattered by the interaction potential, this V of R dash. Here V of R dash scatters this wave e to the power I k dot R dash, and the scattered wave is G of R comma R dash times V of R dash times e to the power I k dot R dash. Okay. Actually, this produces a wave which travels from r dash to the point of observation r. So if this is your point whose position vector is r dash, this actually scatters the wave to the point P whose position vector is r. This is represented by this first term in the RHS of equation number 4. Okay. Now, in fact, if your aim is to find the total wave function arising from this single scattering, how that can be obtained? Actually, that total wave arising from the single scattering is obtained by the integration over the region in which force is effective. It means where the potential field is effective, if you will integrate this result for that volume or for that region, then you will actually get the total wave function which arises due to this single scattering. That is here the incident wave e to the power I k dot r dash has been scattered to this much. This is the scattered wave. Okay. Now let us see this second term in RHS of this equation 4. Actually in this second term, the incident wave is what? You can see the second term, actually in this second term the incident wave is I k dot r double dashed. I k dot r double dash. This is actually the incident wave. Okay. I k r double dash, that will be actually the incident wave. Okay. And this incident wave e to the incident wave is what? E to the power I k dot r double dash. This is the incident wave. Okay. And actually this incident wave will be scattered at the point r double dashed. This is v of r double dash e to the power I k dot r double dash. And this travels to the point r dashed, which is given by g of r dashed comma r double dash p of r e to the power I k dot r double dashed. Okay. And actually when this wave, incident wave e to the power I k dot r dashed is scattered at the point r double dashed, then it moves from the point r double dash to r dashed, and again it is scattered at this point r dashed to reach the point of observation r. Okay. So actually the total effect of all such scattering is obtained by the integration over r double dash to r dash. Oh. And therefore the nth term represents the contribution of the waves which have been scattered n times in the region of interaction before traveling to the point r, where their contribution is observed. Okay. Actually, if the interaction is weak, if you are talking about the weak interaction, so that the scattered wave is not large, then it is expected that Neumann series will converge rapidly and the first term in the series will provide an approximation to the value of psi. And actually this approximation is called First Born Approximation. Okay. So in First Born Approximation, what will be the expression for this psi? This will be e to the power I k dot r minus m over 2 pi h bar square times integral g of r comma r dash v of r dash e to the power I k dot r dash d gamma dash. Okay. Actually, now we will talk about the asymptotic form of Green's function. And as I have discussed earlier in my video, the Green's function, you have seen there that actually when you talk about the asymptotic form of Green's function, that is defined like this: g of r comma r dash is equal to e to the power minus I k dash dot r dash times e to the power I k r over r. Actually here this k dash is the scattered wave function, scattered wave vector. Okay. Now let us substitute this asymptotic value of Green's function g of r comma r dash in this equation number 5. at the place of this g of r comma r dash. Actually, in this condition, we will get the value of wave function psi when we have considered the asymptotic form of Green's function. So what will be now psi? Psi will be e to the power I k dot r. You can see the expression here. This term will remain at it. Now instead of this g of r comma r dashed, we will use this expression. And so this will be minus m over 2 pi h bar square times e to the power I k r over r and integral e to the power minus I k dashed dot r dashed v of r dashed e to the power I k dot r dash d gamma dashed. Okay. So this is the expression for the total wave function. But as you have learned in my previous video, that in case of a scattering, the total wave function is given like this. This is e to the power I k dot r plus f of theta phi times e to the power I k r over r. You know, here this e to the power I k dot r, this represents the scattered wave, incident wave, and the second term represents the scattered wave. And actually in this second term, this f of theta phi, which is just identical to f of omega, that is called actually the scattering amplitude. So now let us compare this equation 6 and equation 7. When you will compare it, you can see what will be the value of f of theta. You can see at the place of e to the power I k dot r in both of the equation, the term is same. So the second, for the similarity of the second term, you can see in the second term of equation 6, this factor e to the power I k r over r is present, and also here in equation 7 it is present. So the remaining factors is at the place of f of theta phi. So comparing these two equations, you can easily say that f of theta phi is equal to what? This is minus m over 2 pi h bar square times integral e to the power I k minus k dashed dot r dashed times v of r dash d gamma dashed. Okay. So in this way we have obtained the expression for the scattering amplitude. But you know, the square of the modulus of this scattering amplitude is called differential scattering cross section. So what will be the differential scattering cross section? Sigma of theta phi. This will be a square of the modulus of f theta phi. But you can see the expression for f of theta phi. So after substituting that value, we get the differential scattering cross section sigma of theta phi equal to m over 2 pi h bar square whole square times a square of the modulus of e to the power I k minus k dash dot r times v of r dash d gamma dash. So in this way, we have easily obtained the expression for the differential scattering cross section. But as I have told you earlier, we must have to check when this Born approximation is valid and when it is invalid. Okay? So what is the condition for the validity of Born approximation? Now we are going to learn. If you want to say the condition for validity of Born approximation in just a sentence, you can say that this Born approximation is valid when the scattered wave is much smaller than the incident wave. Okay? This is the condition. If the scattered wave is much smaller than the incident wave, then Born approximation will be valid. But if the scattered wave is not much smaller than incident wave, it is comparable to incident wave, then this approximation will not hold. Okay. So in mathematical way, you can say that the condition for validity of this Born approximation can be written as modulus of psi scattered of R is much smaller than mod of psi in. Actually here psi Sc, this represents the wave function of the scattered wave, and psi in represents the wave function of the incident wave. Okay. But you know that the wave function of the incident wave is e to the power I k dot r. It is simply plane wave. So this condition may be expressed as modulus of psi Sc must be much smaller than mod of e to the power I k dot r. But you know, mod of e to the power I theta, this is equal to 1. Why it is 1? Because you know, e to the power I theta, this is cos theta plus I sin theta. Okay? And its modulus will be equal to square root of cos square theta plus sin square theta, and that will be equal to 1. So mod of this plane wave is equal to 1, and so you can say that a square of the modulus of psi Sc must be much smaller than 1. This is actually the condition that must hold for the validity of Born approximation. So you can say that if a square of the modulus of psi Sc is not much smaller than 1, then this Born approximation will not hold. Okay. But just you know from the theory of scattering that the scattering wave function psi Sc in general is given as f of theta phi times e to the power I k r over r. Okay. And we have already obtained the value of this is f of theta phi here in equation 8. Okay. So now substituting the value of this f of theta phi, which is actually equal to this much as we have learned earlier. Okay. Now let us put k minus k dashed is equal to kappa. K minus k dashed is equal to kappa. K is the wave vector of the incident wave. Okay. And this is the wave vector of the scattered wave k dashed, and k minus k dashed. K minus k dashed. If you take this direction as minus k dashed, then this will be actually equal to kappa. Okay. In fact, this kappa is also the wave vector of the scattered wave. Okay. So if we substitute this kappa instead of k minus k dash, then psi scr, this is given as this much. This much. Minus m over 2 pi h bar square integral e to the power I k kappa dot r dash v of r dash times this much d gamma, because psi sc is f of theta phi times this much. Okay. Here I have actually used r dashed instead of r because we are talking about the scattered wave. Okay. So in this way we have obtained the expression for the wave function of the scattered wave. Okay. In fact, when you talk about the scattered wave, in general, the scattered waves are spherical. And you know, in case of a spherical wave, the intensity of the wave is inversely proportional to a square of the distance of the point from the source of wave. So with increase in R from the source, this intensity rapidly decreases. And therefore you can say when this R tends to 0, intensity will tend to infinity. And when R tends to infinity, intensity of a spherical wave will tend to 0. So it is obvious that in case of spherical waves, the intensity is highest, it is maximum in the region where R tends to 0. So now let us find the maximum value of the intensity. And you know, intensity of the wave is simply equal to a square root of its amplitude, psi Sc 0 square. This will be actually the maximum intensity when you consider R equal to 0. Okay? So for getting the quantitative expression for validity of Born approximation, let us find the value of this psi Sc at in the region where R tends to 0, so that we will get actually the maximum intensity. Okay? You can see modulus of psi Sc. What will be that? You have to take R equal to 0 in this expression in RHS. Okay? And after that you have to take its modulus. So this will be modulus of minus m over 2 pi h bar square integral e to the power I k kappa dot r dash times b of r dash times e to the power I k r dash over r dash d gamma dash. Okay? But you have seen that this Born approximation is valid when a square of the modulus of psi Sc. Here I have written psi Sc of 0. It means we are talking about the region where intensity is maximum. That must be much smaller than 1. But what is the value of this square of the modulus of psi Sc 0? Psi Sc 0 is defined here. Now let us take its square. So this will be m over 2 pi h bar square whole square times a square of the modulus of e to the power I kappa dot r dash v of r dash d gamma dash times e to the power I k r dash over r. And this must be much less than 1. Okay? And now actually we can find the value of this modulus of psi Sc 0. Okay? Psi Sc 0, you can find its value and this will be m over a square of m over 2 pi h bar square times mod of e to the power I kappa dot r dash plus k r dash times v of r dash over r dash d gamma dash whole square. Okay? Actually here these two exponential factors have been combined. Okay? So when this condition will be hold, then Born approximation is valid. Now if you talk about particularly for the spherically symmetric potential, you know, in case of a spherically symmetric potential, what will be this volume element d gamma dash? Actually, when you consider a volume element in 3 dimension in a spherical polar coordinate system, then you know the length of this element is dr dashed, its breadth is r dashed d theta, and its height is r dashed sine theta d phi. Okay? If you write here dashed in accordance with our supposition, then this elementary volume will be given by dr dash times r dash theta dash times r dash sine theta dash d phi dash. Okay. So now you can find the value of actually here I have mistaken, there should be sign of integral. Okay. Now let us put this value of d gamma dash, d tau dash in this result. Okay. Instead of this d tau dash, we will write this much. Here actually there will be a triple integral with respect to r dash, with respect to theta dash, and with respect to phi dash. Now you can see this result will be m over 2 pi h bar square whole square and the square of the modulus of integral 0 to a. Actually this first integral is for r dash, and we have assumed here that there is a sphere whose radius is a. Okay. So the limit for the r dash is equal to 0 to a. And this second integral, whose limits are 0 to pi, that is for the variable theta, that is sine theta dash d theta. Okay. And the third integral, whose limits are 0 to 2 pi, that is for this d phi dash. Okay. But if you consider that this wave vector kappa makes an angle this theta dash with respect to this r dash, then kappa dash dot r dash, this will be kr cos theta, and therefore when you will evaluate this term e to the power I kappa dot r dash and sine theta dash d theta dash. It means first of all we are going to evaluate the integral with respect to theta dash. So you can see this integral will be in 0 to 2 pi e to the power I kappa r dash cos theta sine theta dash d theta. Actually to evaluate this integral you can use the substitution method. Let us put cos theta dash equal to t. Then if you will take the differential of both sides, this will be minus sine theta dash d theta dash is equal to dt. Now check the limit. You can see the lower limit is 0, it is value of theta dash. So when theta dash is 0, you can see t, which is cos theta dash, that will be equal to cos 0 and that is equal to plus 1. And when theta dash is equal to pi, then t will be cos pi, which is minus 1. So now the limits will be plus 1 to minus 1. But I have written minus 1 to plus 1. Why? Because this here is minus sign, and when minus sign will become plus, the limits will get interchanged. So limits has been interchanged and the minus sign has been omitted. Okay. So now your integral is minus 1 to plus 1 e to the power I kappa r dash t dt. Now you can see this is a very simple integral. Its value will be e to the power I kappa r dash t divided by I kappa r dash, and limits are minus 1 and plus 1. And after substituting the limit you get this much. Okay. Now you know integral of d phi dash from 0 to 2 pi, this is 2 pi. Now let us substitute the values of these integrals. Now only the integral with respect to variable r dash has been left. Okay. So psi Sc of 0 whole square, mod of psi Sc of 0 whole square, this will be equal to m over 2 pi h bar square whole square, and modulus of this much, integral 0 to a e to the power I k r dash v of r dash times this much times 2 pi dr dash. This should be much smaller than 1. Okay. Now actually when you talk about the point near the scattering center, then actually this wave vector k, which is actually the wave vector of incident wave, okay, and kappa, which is the wave vector of the scattered wave. Actually, in the region of a scattering center, these two wave vectors are almost equal. So now let us concentrate ourselves at the scattering center, and at the scattering center you may take kappa equal to k. Kappa equal to k. So instead of kappa here we will now write k, and when you will write k and you will multiply by this e to the power I k r dashed, your result will be this. A square of the modulus of psi sc 0 equal to m over 2 pi h bar square whole square, and a square of the modulus of integral 0 to a 2 I k r dashed minus 1 over I k times v of r dash times 2 pi dr dashed whole square, and that should be equal to much smaller than 1. That should be much smaller than 1. Okay. Now let us take this 2 pi whole square outside of the integral. Then this 2 pi will cancel out. And we will also bring this k outside, and I square, this will be minus 1, and when you will take modulus, that will be plus 1. So your final result is a square of the modulus of psi sc 0, that is the magnitude of a square of the magnitude of the scattered wave function, that is which is equal to m over h bar square k whole square times a square of the modulus of integral 0 to a this much. This should be much smaller than 1. So this is our final result. When this condition will hold, then Born approximation may be applied. Okay. So you can say that this is the condition for the validity of Born approximation. I hope now you can easily write if this question will be asked in the examination, the scattering problem of which is solved by Born approximation. Definitely this video will be very helpful to you, and if you will write the answer in this manner, definitely you will get good marks. Okay, thank you very much.